Campbell. I'm here with Noah Mogensen. We're discussing our capstone project, which was Campus Oracle.
So the goal of our project was to use LLMs to create a chat-like interface for querying information about SOU. This was done as a sort of test case for our client's hardware. We also limited the scope of information that could be queried to the course catalog in order to make things more manageable. So our client, Joe, has a local startup called Grounded AI. Joe got his hands on these cryptocurrency mining GPUs that were previously used for mining Ethereum. The GPUs are very similar to A100s, which is a standard data center GPU, but a lot of the useful functionality of those GPUs were throttled, making them useless for anything but mining Ethereum. Ethereum, on the other hand, changed their mining process, which renders these GPUs pretty much worthless. However, they're still basically A100s, so we wanted to see if the limitations could be worked around, hence why we were running LLMs on them. So what is an LLM? Before explaining what those are, I should probably mention what neural networks are. Neural networks are essentially universal function approximators and are structured as a network of nodes with weights representing pathways between those nodes. The weights are just numeric values that stand for the strength of the pathways. Training a model is just the process of finding the best weight values for our desired output. An LLM, or large language model, is a particularly massive model. The smallest ones are usually several gigabytes in size, and they are trained on natural language in order to ingest and output natural language. We generally needed to run these with some level of quantization in order to fit these onto our cards. Quantization is basically just compression of the model. It reduces the precision of the weight values, and it negatively affects the output of the model, but it allows us to run the models in more resource-constrained environments.
LLMs themselves have a few limitations, which are probably well understood by people who use ChatGPT. The chief one is that they only know what was in their training data. As an example of this, if you ask ChatGPT to generate a class schedule for an SAU computer science student, it will simply hallucinate an answer as opposed to answering rationally because it doesn't know, it has no idea. The other thing that they're bad at is math and logic. Interesting test case for this, open ChatGPT, ask it to list 15 animals, like the names of animals, and then ask it to order those by the number of vowels in each one. And I will bet you that it will screw that up and it will get them out of order because they just struggle with mathematical tasks, even counting.
So the way we get around that is via RAG, or retrieval augmented generation. Essentially, this is just the process of pulling in important information based on the user's prompt and giving that to the LLM so that it can better respond. This is done by putting all potentially relevant information into what's called a vector database and performing a similarity search using the received prompt.
So I'd like to show a little demo of similarity search. So how these things work is that they use a separate neural network apart from the LLM to generate text embeddings, which is a vector in a 1500 dimension space where things that are close to one another in that space are related semantically. So it's not really possible for human beings to visualize a 1500 dimension space, so I've used an algorithm called TSNE to reduce that for our embeddings down to 3 dimensions so that we can visualize it. And what these points are the descriptions of courses at SOU from the catalog. So you can see here we have Introduction to Nonprofit Organizations. That's near business, government, and nonprofits. That adds up, right? That's near healthcare economics. I buy that those things are, that the descriptions of those courses are similar to one another semantically. Policing and Society is near Fundamentals of Punishment, is near Science and Religion. Oh, actually that's not near, it's just hard to see. Networks 1 is near Networks 2, right? Adds right up. So how similarity search works is that your query gets its own text embedding. It effectively becomes a point in this cloud, and then the n number of points near it, the closest 5, say, are given to the LLM as potentially relevant context. So you're sort of handing the LLM on a silver platter what you think it needs to know, or rather what the embedding model thinks is related. Back to the slideshow. The other big problem with these things, with LLMs that is, as I mentioned earlier, is that they're bad at logic and math. So something like generating a course schedule where things need to happen in a particular order and there are really concrete requirements is something that it'll struggle with. Our idea, and this is really where we got into sort of experimental territory, was tying an LLM to a constraint model. Constraint programming is a really powerful tool for mathematical problems, but it's difficult to use. So another way you could think about this is we were using the LLM as a natural language front end to constraint programming. The idea being that the LLM could generate constraints for a constraint model in Z3, say, which is a constraint programming framework, and hopefully you get valuable results out of that. So this is a quick demo of, unfortunately not that quick, and we'll get into that, but I'm going to play this at double speed of our product. So I'm telling it I'd like to generate a course schedule. So it is using really a primitive form of retrieval augmented generation, not semantic search, but it's reaching out and calling a function, actually. The LLM can call a function to get the information it needs to know about the catalog. So right now it's because I'm trying to generate a course schedule, it has to know what classes I want to take, and now I can ask it about particular classes. It's presented me a list of alternatives for CS electives. I'm asking it about one of them. And as you can see, it's not a command line interface, right? It's just natural language. So part of the reason that this is slow is because we ended up, for reasons we'll get into later, settling on GPT-4 as the LLM. So we're really just at the mercy of OpenAI and how quickly they feel like responding to us. Okay, so we've got those chosen, and now it's giving us a list of alternatives for our humanities classes, and I'm telling it my preferences. Okay, yeah, now we're into the G strand, and this is where I realized that the viewer was probably getting bored when I recorded this. Oh no, sorry, this is F strand. So part of what's interesting about this is you can see that it's really just conversational. This is where I realized the viewer was probably getting bored, and I said, let's just let the constraint model pick stuff that will allow you to graduate for the rest of it, because the audience is probably getting bored. So this step is where we get into constraint solving, is where we get into constraint programming. What's happening right now is not the LLM generating the schedule. The constraint model, written initially in Z3, though later ported to a tool called CPSAT, is generating the course schedule based on the actual graduation requirements. So this is more or less guaranteed to be correct per the model that, the core model that I wrote. And there you have it. This is everything a CS grad or a CS student needs to graduate. So here, this is a demo of similarity search. It is not just searching for the string Middle East in the catalog. It's actually using semantic search. And as you can see, not all of these even include, oh, I suppose they all do include the words Middle East. Well, no, IS 250, the actual description of that course, did not include the words Middle East. It was just assumed that it would cover that because it's international studies, and the semantic search picked that up. Oh, there we go.
So what we used to make this, pretty much everything was done in Python. We dabbled in C++ for some parts, but it was all Python by the end just because the bindings to libraries we needed were so good. Llama.cpp was the library we used to run models locally. Docker was used to containerize builds on the server. Docker's pretty great. Postgres was used for the vector database. There are vector database services out there, but a lot of them are pretty new and are subscription services. Postgres, on the other hand, is really old. It's pretty common in the industry and pretty rock solid. So we decided to use that partially for that reason and partially because we learned a bit from setting it up ourselves. We used the pgvector extension for the vector database part. The server was configured with Ansible, and we did make heavy use of the OpenAI API. That was part of our work during the spring term, was migrating to that API because the industry is sort of coalescing around it. Lots of services are sort of offering APIs that are compatible with OpenAI's API because they're so dominant. So the hope was that we would be able to sort of hot swap between those different services. So by the end, we had a LLM RAG to constraint programming pipeline using the SOU course data, and we experimented with some novel methods, and we did use conventional RAG methods. We tried local models, and we used the best commercial models that are available right now. The local models did not perform as well. The commercial models performed better. And as far as the hardware goes, it performed pretty well. Once the models were quantized, inference was fast. The only issue was the memory on the cards.
So this project kind of came apart in some ways. And this slide is my intuitive understanding of what happened based on growing the project from sort of a toy into something more real. And what I think I found was that as you ask LLMs to do more, and as you give them more leeway and more different actions that they can take through function calling, the odds of them screwing up increases. And there are ways that you can sort of decrease the slope of this plot here, you know, odds of screw up versus scope of task. And we did a couple of those. We did prompt engineering, which is where you carefully write the LLM prompts in order to give it the best chance and to have it understand the task as well as possible. And we also migrated to a smarter model. We found that the open source models were simply not capable of doing what we wanted, and indeed, that GPT-4 was not as smart as we thought coming in and was not really capable of everything we wanted it to do. So in the end, what we did was the surest way to make it as reliable as possible, and that was to really put the LLM on rails and give it just a sort of linear set of tasks to hit. And in the end, that felt a lot like programming. I think that the benefit of using an LLM was really lost in a lot of ways because it was so constrained in what it could do. But the fact is that it just wasn't smart enough. It wasn't as smart as we thought at the beginning to give the thing a lot of leeway with the constraint model, say, right? One thing we found is that even with the best commercial models, so GPT-4 in our case, it can still melt down. If you look at line 12 and below, this thing had everything it needed. This is not a bug on our end. It had the correct list of course names, but I think because we were pushing it and we were giving it a ton of information and a ton of things to do, it sort of had the AI equivalent of a seizure and just generated nonsense. And it's interesting that these kind of, in some ways, look like real course names. Like they have the sort of rhythm of real sentences, but they're just nonsense. Some of them aren't even, you know, a lot of them are not even real words. And when you're doing function calling, that's especially pressing because you're asking it to write code, or rather, when you're doing constraint programming, you're asking it to write code, and you're giving it a lot of leeway to screw up. This was the result of GPT-4 attempting to write CPSAT Python code, and it's nonsense, as you can see. So I think if we were going to extend this, there are sort of two directions you could go with it. One would be as a research project, and the angle there, I think, would be to use advanced techniques to improve the LLM's performance, and that would be making several passes with the LLM, or using a multi-agent architecture where it's like multiple LLMs in a conversation with one another. We didn't do either of those because our main goal was to see if we could operate in this resource-constrained environment. And adding more LLM calls is not the way to do that, right? The other problem, as you saw, was that latency is a big issue. So if you're going to have, maybe 6 LLM calls for every phase of that conversation, you're multiplying the time this takes by a factor of 6. Another angle would be to experiment with other constraint programming technologies, or sort of try to make the interface between the LLM and the constraint framework more flexible. As a product, if I was just trying to sell a catalog assistant to SOU, I would take the LLM out of schedule generation. I would leave the LLM in for semantic search, for RAG, so that the student could query documents related to SOU. And then I would use the constraint model, which, not to toot my own horn, but was not easy to write, and make that its own thing and just build like a React app around it. I think that's all we have to say, Noah.
Yep, I think that covers everything.
Yeah, so this project, I think the final product didn't end up being everything we hoped, but I think that we covered a lot of ground in terms of experimenting, and I think that was really valuable for both of us.
For sure. We learned a lot from the project.
Yep, thank you.